screen is now being recorded. All right. So there, yeah.
The coil expansion factor, is it a constant?
No, that's what you're measuring. You're measuring the size of the coil, right? So, so it's R, the actual size of the coil to the condition R theta. So like the theta is like that point where you let's see. Like this. So it's like this. All right. So this is the wrong plot, but kind of close. And say the theta would be like somewhere halfway down the curve, like in that other plot. So in this case, it collapses on heating because it's an LCSD. And the other one collapses on cooling. The polystyrene cyclohexane is a UCSD, meaning it phase separates when you cool it down, like a normal system's UCSD. It's a U-shaped thing upside down, and the peak's at the top. So it's called upper critical, even though it's a lower temperature. And the other one, the peak would be upside down. So when you heat it, so it's a lower critical. All right. So right, so here you're heating up and it collapses. The theta is like right here. So this would be, if you divided this by R theta, which would be that value, then, oh, in fact, it's 1. So I'm not sure why it's 1 there, but basically this is already normalized. So it's 1 at the theta temperature. So he's got, this is kind of alpha he's plotting. So it's 1 at the theta temperature. And then it goes below 1 when it goes to collapsed. Right? So it's going to be a small number when it goes collapsed and get larger when the coil is expanding. For LCST, it goes that way. For UCST, it's the other curve going that way. Right? And I think these guys are all LCST, right? We're seeing the collapse on heating. Yeah.
The other plot, why the cooling and heating is not fine?
This is one's hydrodynamic radius, and one's radius of gyration. This one down here. Oh, the original?
No. The same slide.
Okay.
The other slide.
This?
Yeah. Cooling and heating. Why?
It's a hysteresis because of things. This paper's so when a protein folds, okay, it's in an expanded coil state and then it collapses, but it isn't folded to a functional form. Like it doesn't have the lock and key thing that it needs for an enzyme. So it has to go through a thing like called a molten globule, which is a 3D object that's gooey, I guess. That's what globule means to me. Well, yeah, you think that it goes to that, and then all the disulfide linkages and the polarity and the hydrogen bonding happens, and then it self-constructs into this perfect shape. So you can take that; it's a perfect object, absolutely perfect, right? So and then all of them are exactly the same once it folds like that. So you go from a thing that's like to something like, and it's just like a perfect object, right? So that's the transition between. So that takes some kind of something happening. That takes time, or it takes something. Anyways, hysteresis means that something, the process is different on folding and then on unfolding. It's like it's autonomously like folds together, and then when it releases, a different process. So it's got a difference in size and it takes time to reach. Once it gets to the fully expanded, it's the same. It's a good question. I mean, there's a hysteresis in the curves. This paper, if you read it, it's good paper. I didn't use it, but it's 1998, so it's a while ago. So I'm trying to get current things, but it is a pretty good paper. And this is a series by this group where they go through this stuff. So they were able to make these molecules. They could get the second order transition, like polystyrene cyclohexane. They can get a first order that has a minimum here that has to do with the kind of the enthalpy of transition. They get an overshoot. It's discussed in this paper, and also because they measured RG/RH, the ratio has certain values for certain objects, like 0.774 for a sphere, and for an expanded coil 1.6. So they're getting numbers of that ratio like 1.6 and then something like 0.7. So you can tell from that ratio kind of if you have a sphere or expanded. So that's kind of common to do, but anyway, so that's kind of overview of that stuff going on. Yeah. That's a good question. The voids in proteins is a whole subject of its own. But yeah, the idea is for us is it has no voids in it. But there's studies that people do about so there's a series of papers about, and people have spent their whole career looking at voids and folded proteins, because supposedly it's like a vacuum. So there's like and then they talk about the vacuum things, and apparently it's important. So they take a protein and put it under high pressure, super high pressure, like 40 megapascal, some 400 atmospheres. And they're like looking at how that void stuff changes. I mean, so people are doing void things with proteins, but the idea here is that it's totally collapses, no void. But there are voids in it, and it's folded. Anyway, so anything else here?
The Monte Carlo simulation will be applied to transition of.
Yeah. Yeah, you can use Monte Carlo, but these people, all the papers for this week are all lamps. So you can see lamps is just like pretty easy to use. But they'll also use CHARM, CHARMM, is like the real biophysics guy, because CHARM can handle water better. So if you really, so it's kind of odd that they're using lamps here, but they're doing really model systems. So they aren't considering water. So water is going to have a key effect in all the bio stuff. And lamps can't handle water. Water is going to put a huge load on your computational time. And and also getting it right is really difficult. The interactions of water, because it's like a V thing, and the two polar and the plus and minus. Anyway, getting that right in a molecular dynamic simulation is difficult. And then there's a lot of debate over if they got it right or not. And getting the density of water right after that. So it's a huge like can of worms to go into. And doing lamps is just like click, click, boom, play the video game. So it's much easier, even though, so it might not be true. So they keep saying over and over again, this is like simplified. To you, it isn't simplified, but it's actually much, much simplified versus what the actual biosystem consideration with water would be. So anyway, so anything else in that? All right, so I'm gonna get rid of this, figure out how to get rid of this. And go over here. So we got, so this 3 papers I put up. Let's see. So this is paper this is a one 2024. So I'm trying to find a recent paper, so I got this paper. It's not necessarily the best paper, right? And also, he's relying heavily. So they're also from 3, like all 2 of them have in Korea connection. Then this is all European, I guess. And then there's a US Korean, and there's someone else Korean. This is US. So Ha is in the US somewhere, right? Department of Physics and Astronomy, Waterloo. Oh, in Canada, Canadian Korean. So he's a Korean guy. Ha's a Korean name, and there's other Korean people from this department, from the Institute of Advanced Study. So Princeton invented this Advanced Study Institute to attract Einstein and some other people to Princeton. And it's kind of like a place where you don't have to do anything, and it's surrounded in a forest, and like the birds and deer hopping around and stuff. Anyway, so since then, there's I think 54 advanced institutes around the world. All of them have hopping deer and fish jumping out of the water. And then like they sit in some kind of idyllic place and dream up whatever. So Korea has one too. So it must be like Korean fish or something, But anyway, so it's kind of interesting they're from there. And then Ha is from there and then goes back and forth to this Waterloo, which is a good kind of an engineering school in Ontario. It's a pretty well-known place. So this paper is really well written. This would have been a good paper, better paper to do than the other paper. And also the other paper's like borrowing really heavily on this paper. And it's hard to tell exactly where he's actually contributing this Chambouchet, where he's actually contributing beyond what Ha did. I mean, so for instance, so his main point of contention is that, so Ha comes up with a theory. So I'm kind of more of a Ha fan. So Ha comes up with a theory, he doesn't call it the Ha parameter, but this Chambouchet does. And then this is is this figure 1? figure one, so figure one, this figure. So he shows the swelling ratio alpha, so R versus R theta versus this parameter that Ha came up with, the concentrate. So what he's doing is he's adding in low molecular things. They can be salt molecules, they can be a protein, they can be particles, like colloidal particles. So basically he's putting something in. So he has his simulated polymer, they have monomers of some size, and hopefully these things are smaller. If they're larger, you don't get a discrete transition between the collapse. So you get this kind of continuous transition. And that's the case for polymers, because usually these things are colloidal particles when you add them to a polymer. That's our argument. So polymers usually have a second order because you're adding colloidal particles. And with proteins and RNA and DNA, the collapse happens when you have smaller things around it. This could be DNA, and these small things could be proteins. So they're smaller than the kind of units of the chain. Anyway, so the main thing that Jean Boucher is saying is that, oh, look, all right, so this Gian and Shendrick is the Ha paper. So they're using two different molecular weights, 50 and 15, and it's small numbers. Then they get, so if they plot the swelling ratio versus the Ha number, oh, they look exactly the same, right? In other words, it doesn't matter molecular weight. But his main point is, well, the circles deviate from the triangles. Like that deviation is what he's arguing about. And in the end, he brings that together by assuming this goes to 1. He sets this, normalizes this, gets it to go to 1. I mean, in his argument, he forces it at this end to go to the same value, and then the other end, he says it doesn't work at the high extrapolation limit either. And I mean, it could be noise or something, I don't know. Anyway, it looked to me like it's a perfect fit. Like this is, to me, like as good as you're going to get from this kind of course. So his whole point of contention is the molecular weight dependence of this thing, which Ha says there isn't one, essentially. Ha doesn't say, though, he claims that Ha says there isn't one, but if you go to the Ha paper, Ha does explain the molecular weight dependence, so that actually this whole thing makes you wonder whether you want to believe the French guys or the guy from the US. Anyway, so Ha's a better paper to read, and he explains the whole field pretty well. So he's talking about this AO, let's see, Ashok Osage, something I think it's called. Let's see, I gotta make this larger. Somewhere he gives that word that I can never remember. It's like Japanese names. Anyway, there's an osmotic effect. So let me show you what this looks like. So we have, oh, they're like generating paper here. Every time there's more paper, I have to consume it faster. All right, get smaller. That's good. All right, so I think I said before, like, so if you have colloidal suspension, so you have, it could be like salt and water, it can be polymer chains in water, it could be surfactants in water, it could be anything that's dispersed in a fluid, right? So this you can say that that's the same thing as if you have gas atoms like moving with KT that generate a pressure. When they hit the walls, they make a pressure. Right? Oh, it's not focused. It'll take a minute to do that. Doesn't want up there. It always takes like a second. All right. So anyway, the kinetic theory of gases is like that the particles moving around, they bounce off each other elastically. So one will come up and it'll just bounce off if it's flying in. And then they hit the walls of this container, and that hitting the walls process generates a force that leads to the pressure in the system. So the idea is like, well, these things look like they're moving around by KT if they're small enough, and then basically if they're less than maybe 10 micron. So it's a fairly large, and down to like an angstrom, or even probably maybe an angstrom, like as small as you can get, like atoms, right? So basically those things are moving around. And if you compare that with the absence of it, there's a pressure associated with that thing, which you can demonstrate if you have a semi-permeable membrane that only allows the fluid to go through, but not the dots. So you have one side with dots. The fluid wants to dilute, so it's going to drive over there. So one way to look at it is the fluid you want to have an equilibrium. You want to have the same concentration on both sides, but the things you're trying to dilute, you can't pull them over because there's a semi-permeable membrane there. So it just has to pump fluid over like that to try to dilute it. The other way is you can just calculate this pressure, which is usually called pi. So it's going to be like N RT over V. Or if you want to say N over V is rho, so like the density and rho RT. Right? That would be the first. That's like the first. If you do a viral expansion, that's the first viral coefficient. And if you want to say like a real system, we have B2 rho squared, and the third one would be like C, or B3, which we call C here. So it's like B and C, rho cubed. Right, so that's it. That's the whole idea. Like, and we know that for polymers, B2 is the volume of the times 1 minus 2 chi. Because you take the 1/2 out. I mean, it's really 1/2 minus chi that you do in the equation. Take the 2 out to get the B2. It's that. And then B3 is a little bit unknown, but it's going to be kind of volume squared or something times some other things. And so that's kind of the scheme of this osmotic pressure. You have this thing that happens. So if you go, so is that clear enough? Or like you have this kind of analogy between gases and colloidal suspensions, and polymers could be in the colloidal suspension. So the advantage of this is N, right, is number, how many. So this is a quantitative, by measuring the height of the fluid going up, it's a quantitative way to measure the number of molecules that are in there. And you know how much goo you poured in it, you weighed it before you put it in, then you know the mass, divide by N, and you have the molecular weight. Because it's number, like you're counting, so it's called colligative. Colligative is somehow, some language means counting. I'm not sure which language, probably Latin, I guess, but anyway, so colligative property means you counted the stuff, and this is counting the stuff. So if you look at the molecular weight distribution, so the number average is like the mean. That's the number you kind of want. You know, if you do light scattering, you get the weight average, that's higher. And then if you do viscosity, you get the viscosity average, that's even higher. That's like, because it's a 3.4 power, it's like the third moment, 3.4 moment of molecular weight you're looking at. So that's higher than the 2 you get from light scattering, and much higher than the 1 that you get from colligative property like this, right? So this is kind of a nice number to have, because it really is a number you kind of want when you're looking for molecular weight. What's the average number? This is it, right? So it's a simple measurement to do, right? So it's like melting point depression, freezing or boiling point shifting. Those are all colligative. They're related to the number. So anyway, so if you have your bead thing, and then if you're AC, the Crowder thing, and the A, the polymer chain thing, if AC is smaller than A, then you have this situation where these beads, because there's an excluded volume, so these beads can only go till they touch. That means there's a region where you can't have beads. That means there's an exclusion of the colloid thing from the polymer. So that means you have these regions with nothing in it, which is just like a semi-permeable membrane. That means you're going to get a pressure. That pressure creates a vacuum in this hole, and that can lead to collapse of the chain. Right, so that's kind of this AO's theory, and then you can see if the A to AC ratio changes, this behavior changes because the excluded volume gets different, right? So that's the yeah. I couldn't hear. A is a Crowder, and A is the thing. A is so there's a thing called a Crowder, CROWER. So they're talking about these things as Crowders. Someone named them Crowders. So they're kind of crowding around the molecule, I guess. And then they cause this depletion effect. When you have the depletion, there's an osmotic pressure created. That osmotic pressure pulls the blue things together, and that makes the thing collapse. That's the problem, that every paper uses a different nomenclature for this. So the one paper calls AC small d and A big D, and one of them uses sigma for A and for big D. And then one of them uses D for two different things in the same paper. So the whole thing's, in terms of terminology, it's, oh yeah, A equals sigma. All right, he says A equals sigma here because sigma is what you use in lamps. When you talk about the size of the thing you're looking at, it's called sigma. So you have a potential field, hardcore, it goes to sigma. Sigma is a size. Yeah, so A equals sigma. Yeah, so sigma is another term we can use for it. So it's like a lot of that, you have to figure out how the things match up. I think I wrote somewhere, I have like 10 pages of notes on these things. I'm not sure that it's of any use. When I go back and look at it, it's kind of like, what does this mean? All right, so we got, maybe I should just write something down. So it's pretty confusing. I have them listed here. At some point I just started listing to figure out what everything was. It's a light like that. It's better. We have the monomer size is D. The distance, so one of them, the paper we're using, the Chamberchet paper, has a distance between monomers. So you have monomers of size D, and then they're kind of separated by B. Right, so the reason he does that is because they're thinking about the aspect ratio. Like if he said the chain was a tube, then D would be the diameter of the tube, and B would be like the length. So DNA is like a flexible, so DNA, if you do, I think he does B by D. Must be D by B. It's either D by B or B by D.
D by D.
Is it? All right, that's good. All right, so that's going to give you the aspect ratio, which is small for DNA and large for protein. This protein is going to have the carboxyl and the amine, and then the alpha carbon, and then some big R group, So the D is big, but the B is small. So that kind of the aspect ratio is different between the things. It changes how they act somehow, right? So you can think of, if you're thinking of synthetic polymer, then D by B equals 1. I think he says that at some point. So at some point he just says D by B is 1, but he uses it as a parameter so you can distinguish between proteins and DNA. And then he has this alpha, which is so there's a theta or a theta C, they're the same thing. So theta C is the concentration of Crowders, theta is the concentration of Crowders. But one paper calls it theta C, one calls it theta. And then because that's what I have here, there's others. So he has these in the paper, the Shadrach paper, which is the one we're looking at, he's got these two things. The dimensionless, not dimensionless, but actually dimensionless parameters that you can talk about as these things scaling. So the Ha paper, the guy from Ottawa, D by D. So he has B by D and D by D, they're two different things. D by D is the alpha by alpha C. Right? So it gets pretty confusing because there's a D here, there's a B and D. D is the same, and the small d and the alphas, it gets pretty messed up. And the other is this Kong paper, which comes up with R0, which is the coil size at the theta condition. And then phi is the Crowder composition to the 1/3 D as a parameter of interest. So what's the difference between those two? So the difference is, Kong shows that here. If you want to say, so so there's a difference in philosophy. So the particles, the colloid particles can come into the coil, then they act on a monomer. So they're not acting on the coil as a whole, they're acting on the monomer. And it's that interaction with the monomer and the fact that it causes this collapse that drives this effect that when you add in salt or other particles, the thing collapses. And the other case is you can say that they can't penetrate the chain and then they're outside, and somehow that causes the thing to collapse. Yeah.
But if the colors are stay inside the polymer.
That's allowed. I mean, it's allowed. I mean, it's basically, it's a cutoff point. So, it's a continuum in the theory. So there's not a discrete thing that happens there. The behavior changes there. Like the behavior is different for the large crowders and for the small crowders. Right. So then, all right, so there's that issue, this kind of already complicated issue to the thing. I mean, the collapse itself is complicated. Then adding on this Crowder thing makes it more complicated. Then there's the issue that, so this is the E. coli chromosome. So the chromosome is like the X and Y things. So it's something you can see in an optical microscope if you stain it. And they're called chromosome because they suck up pigment if you stain them. So they were observed in the early 1800s, I think. You know, that's when the name stuck. But basically, there's a nucleosome kind of shell around it, and then inside is like your RNA and whatever. And there's 30% Crowders in there, which are proteins and other stuff, right? And then you have your RNA, which is the active functional thing of the X and Y chromosome, right? So anyway, so they say that's a tube. You can stick your polymer in the tube and put in different amounts of Crowder. So you want to take this thing from 3 meters, 2 meters long to 20 micron. The RNA in there goes from 2 meters to 20 micron. So that's 1,000,000 times compaction. It's quite a bit. So basically, the thing's really collapsing down to some solid object, you know. And part of the reason it can do that, they're saying part of it is this theory from the Grossberg, and part of it is the theory they add in these Crowders and that impacts it. And this kind of AO is 2 Japanese names is A and O, but that can drive it even further. Like this can, so you can have the original Grossberg thing, and then this thing can drive it further to the point where you can kind of control this. So there's also, so the DNA isn't, or RNA isn't like homogeneous, but also it can be, it's usually a cyclic RNA. It's not a linear chain. And then it's not all like polystyrene. It's like all different polymers along it. Like each monomer is different, right? So I forget how many nucleic acids there are, but it's a lot, 27 or something, I think. So basically, it's not homogeneous. So you can get like local collapse of regions that are less thermodynamically favorable, and then anyway, so it can be a lot more complicated than what they're talking about, which is just a bunch of beads. And so, but and they mention that, like if you read this, they go on and on about that stuff. So it's kind of interesting to read. But it's a lot of material, and it's also kind of dense, you know. So anyway, so they're doing a lamp simulation. Everything they do is exactly what everyone else does. Like this is a Leonard Jones potential. They don't want to see, they got a lot of action going on, so they want to truncate it. This has an attractive and repulsive part to it. So which complicates the let's see. So Leonard Jones is like repulsive, like it's got a well, so it's got this well to it. You have the potential, and you have the distance that you're going from the thing. There's like a sweet spot there. This is repulsive. This is attractive over here. So basically, they want to, if you can do, and when we did the DPD simulation, they said that potential is going to be a straight line and just end somewhere at our cutoff, right? And just go to infinity. It doesn't have this local. So it's just repulsive, and it's a straight line. That's DPD, and then dissipative particle dynamics. and then this is Leonard Jones, has this more complication because it's got these things, so they want to just cut it off here, RC, and their cutoff point is is 6 to the, let's see, it's 2 to the 1/6 power, which ends up being like 2 to the 1/6 power ends up being like 1.2 or something of whatever R is. So whatever kind of capital D is from our thing. So it's like almost nothing, like they have the sphere and they go out 20% of the sphere and then they end their interactions there. That's going to be a faster simulation if you go to infinity. Right, so it's, and also it's only repulsive, so it makes it much simpler. Right, so then, all right, this is standard. If you look in all the protein simulation stuff, they do exactly the same thing. Right, so anyway, so and they also use you can look these things up if you want, you know, but basically that truncated Leonard Jones calls Weeks Chandler Anderson WCA potential. Chandler's kind of a famous guy. I don't know about the other two. But Chandler was like a Berkeley guy that did interaction stuff. So anyway, I think he's dead. So then between the beads, they have this basically the spring model where K would be R over NL squared, like from our potential thing, and then they put in a thing that ends it, so it can't go stretch to infinity. So it's a finite extension. This thing makes it finite extension. And then that's just plug in from lamps, like Phen A, just say use Phen A, and everyone uses that. And all the definitions of the relaxation time and everything are standard. And they use this Verillo method to integrate blah blah blah. You can look that up, but basically it's just a plug and play in lamps. You say use a Verillo, and everyone uses the same thing. So this is all standard, and all the 3 papers use the same simulation essentially, you know. So it's just the results that we care about. So they can get the transition. So this is let's see, which one is this anyway? So they're kind of doing the same thing. This is the Ha one, so we don't want to look at, so that's as far as I want to go with Ha, I think. Let's see. So he can get, versus his Ha number, he can get perfect match. Like it's done. The deal is done. He's finished, you know. He can get perfect matches of everything. If you read this paper, you figure there's nothing more to do. So he can, so if you know the potential energy of interaction, you can calculate the second viral coefficient using this thing called the Meyer function. So you integrate the 1 minus e, this is a Boltzmann factor, and integral of that gives you the second viral coefficient. So basically they can calculate the second viral V versus a theta condition versus his Ha parameter, and then he can get a theory to follow along that. He just uses a Taylor series expansion to predict that. Then once he can predict that, he can plug that into the this is the same, or he plugs that into kind of the Grossberg function, you know, for the expansion in the coil. That's, I mean, the Ha paper is pretty good. It's kind of worth reading, but we're not really looking at that one. This is another paper, and then this is the paper we're looking at. So let's see. So this guy goes through the whole, I'll either show him, all right, this is a much harder paper to read. The Ha paper is like, you can decipher it, you know, if you read it. This paper, you can't read this paper first exactly. So I read this paper first. I got little out of it. Then I read the Ha paper, and I came back and read this again, and then I got more out of it. So I still don't have everything out of it, you know. All right, so one thing is that he shows this, so we have the Flory, he says the Flory equation, that the energies, so what we have is the energy is going to be 3/2 R squared over NL squared, but he has this other term. It's like, what is that? So if you remember when we did, this is a question on the thing, that's why I'm saying it, but we did exponential minus activation energy over KT for the Boltzmann, and exponential minus R squared over NL squared. And then we said those two would be equal, and then, right? But there's actually a prefactor here, right? So you can say the arguments would be equal, but what about this there's no prefactor here, but there's a prefactor here. So when you do that, you say EA over KT equals R squared over NL squared. there's actually another term, like, so this is actually the log ln of exponential of that and ln of that. So you have an ln of this and they add together. So you have plus log of whatever and the thing in there and just being alpha. Sorry, that isn't showing up. I guess I shouldn't have turned the light on. Oops, freeze was not a good button to press. There, that's probably better. Yeah, right. Right, so anyway, that's the answer to that. Like that's the prefactor, and this ends up being alpha. So he has log of alpha stuck here. You could kind of figure that out, except it's hard to get this NB squared part of it, or one part of it I couldn't get. But basically, the idea is that's a prefactor. And you'll see that term in other things. So if you convert that to the Grossberg, you turn it into alphas. So alpha squared r squared of NB squared, and that thing's alpha. And then he can when he writes out the Grossberg thing, he ends up with this, and he pumps in this D by B thing so we can distinguish between DNA and RNA. Right, that's also a question in the thing. So, so what's the gist of it? I have that written down. I have 10 pages of this stuff, and then so and one of the questions is like, well, how does it differ from Ha? And it's hard to figure that out. Like, somewhere it says like, what's the difference? His contribution beyond what is shown by Ha. So anyway, equation 11. So he does kind of the same thing. See the collapses. This is repeated. This is Ha's plot, except you see he's normalized his to 1, so it converges here. Then he gets it to converge there. He does that by messing around with the Grossberg function, basically. But there's a lot to this. It's hard to tell if you can actually do this homework, but we can try to just see how far you can get, I guess. So equation 11 predicts alpha from knowing, let's see, equation, I have to step. Predicts r by r0 as a function of nu, right? So this alpha is r by r0, and that's the second Viral coefficient nu. So he can run this simulation and get alpha. Like his point of his simulation, he gets alpha. And then he can plug that in alpha in here. If he knows D by B, then he can get the second Viral coefficient from it. Right. So that's number one. But he takes his results and that's number two. He's going to use that equation to fit. And this is just the equation from Grossberg. Right? So you're going to take that and fit and then get nu by nu 0. Then you can plot and then nu by nu 0 and 12, then you can use nu by nu 0 in the Meyer function to get this energy. So the Meyer function and the same Meyer function to integrate to get the second Viral. He figures out that this thing is actually related to D and D and this energy thing here. Energy would be, he uses the square well potential, and energy is the well depth. We can get that well depth. Then he can, and he uses the energy fit BE that he got from that. So this is a long series of things that you can't exactly follow in one brain motion. Like boom, 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 and when you get to boom, it's like, what's going on? That's exactly how I feel about it. But and then anyway, he fits BE to equation 15, which is this thing. So he comes up with a theory about what this BE should be in terms of a parameter C. So C governs the whole thing. So C has a value of 2.223 with no units. And then so it's complicated and almost like becomes meaningless at some point. But so anyway, I don't really follow exactly the reasoning here. So he's got BE0. He finds regimes when this is small, when the concentration is smaller than this parameter, it's related to the Ha parameter, and otherwise he has that term. And then he can calculate this term from the original AO theory, the Japanese guys, which is in Appendix B, and he gets a cubic thing, and they get a linear dependence on this D by D. So he's kind of saying he's figured something out beyond what the Japanese guys figured out. And then because he has that equation, he can use that to fit the results that he has D by D0 and XC and phi. So he can plot the potential versus that and then use this equation to fit it. Or he can actually calculate, so his calculations of the dotted lines, things from the simulation are the points and they match up. So then he has a holistic view. He can normalize this nu by nu zero, get it to converge at the end points. And then he can say he has a gradient in here. So he doesn't have a function that predicts all the different, again, there's like no difference. Like the points are like the same, like that would be perfect convergence for me. But he says he can predict that gradient for this function, and that's his success beyond Ha. So it was perfectly fine before this, like it seemed to be useful. If you read Ha, it's very useful. Then you see this, it isn't really much of a contribution, I think. He goes on. So he goes on to use that new theory to make this, which is like a phase diagram. So he's got d by d, and then the concentrate, phi is always the concentration of the Crowder. So there's no polymer chain concentration. There's just one polymer chain. And then he's putting in more Crowder with no real concentration of the polymer chain. And using his theory, he can predict where it's going to be. He can predict this line that distinguishes between collapsed and uncollapsed. And he says when you put more and more concentration, the Crowders jam together and make kind of a glass. So he has a jamming transition, which is a paper that describes that. This paper, which has 850 citations, I mean, like this is the Bible of jamming. Jamming's a topic in physics. Like if you go to the physics meeting, they have a whole session run for 5 days on jamming every year for the past 50 years. And it's dominated by French people usually. Like where these Italians, it's like Europeans, and a couple people that like NIST and stuff are interested in jamming. Some protein people are into the jamming thing too. And he has this jamming thing, but the jamming thing, if you look back at Ha, is he already mentions jamming. He calls it something, he says like dynamically slowing down or something like that, but it's jamming. It's like he's kind of repeating in his highlights, he's repeating what Ha has already done a number of years ago, 2016, so 10 years ago. Right. So 10 years ago, Ha did this stuff. Then this guy is coming along and like doing kind of the same thing with a little bit of a twist to it. That's my impression of this paper. And as far as like a general result, it's nice he has this phase diagram. So everyone's trying to make a phase diagram, and like in polymer nanocomposites, well, they have different sized particles going to a polymer, you mix them, they have different regions, they'll make different structures. We'll go through that if we have time. But basically, everyone wants a phase diagram, and then they publish a Nature paper on it. So it's like a governing diagram that people can use in their overview slides. So he has this phase diagram. It's weird that this is the main point of the paper and main contribution really, but he puts it in a little teeny corner of a larger figure. It's a little bit strange. Like he should have made this a highlight and put it at the front of the paper as a picture for the graphical abstract, but he didn't. So it's a little bit strange. Anyway, so it's a lot. I don't know. You can email me about questions about it. I think there's going to be a lot of wandering around in the dark here. If it seems to be like too much, it's okay. It's just to get a taste of the field, I think. It seems to be a lot in here. I mean, you might be able to, yeah. Yeah. I'm telling you to glance at that and see what you can garner from it. Or you could do this. I glance at it, see what you can garner, and then take this thing and put it into Chat GPT and ask it that question or something, and then see what it comes up with. That would probably be the easiest way, because I think that's a pretty long paper. Like it's actually a review paper, right? And it's a book. It's like people write review papers, they don't want to publish a book, they just throw it in the reviews in modern physics. So it's basically a book on jamming. It has 850 citations, so this is like the Bible of jamming. So I don't know how many pages it is, but anyway, yeah, don't kill yourself, but just try to expose yourself to some things that are going on. And like when people talk about jamming, then you're going to say like, oh yeah, that's that 850 citation paper with a lot of French people doing it. So something like that. It isn't like you have to totally. So, so much for 9 pages here.